Hello everyone, welcome to the lecture 19 of the course Diffusion in Solids. So, last few lectures we talked about the atomic mechanisms of diffusion, the correlation factors, and now we will also talk about, so we have although introduced a little bit about how the temperature affects the diffusivity when we talked about the migration barriers and so on. But we will now today talk a little more detail about the temperature dependence of diffusion as well as the pressure dependence of the diffusivities. Although for the solids, the pressure dependence is not of that much significance as compared to the temperature effect, whereas in liquids and gases it can play a more important role. So, if you recollect, I think in one of the previous or the very first lecture, I had asked you to do an activity basically to put a drop of ink in the water, hot water and cold water, and see if you can observe any rate any difference in the rate at which spreads. So, here is a small video you can see, for example. And you see here, so this initial drop, remember, this is just due to the weight itself. Okay, don't think that it is diffusing yet. Okay, so this is the cold water and this is the hot water. Now, in the cold water, you can see that the ink has actually settled down once it reaches the bottom due to the weight alone. Whereas in the hot water, you can clearly see the spreading of the ink at a much faster rate. Okay, I'll just play for you again. You can notice that here the ink has settled at the bottom almost, and whereas in the hot water it starts spreading almost instantaneously, and it spreads much more than in the cold water. So, this is just one simple effect you can also try out at your home. This you actually also observe in your daily life. For example, when you mix let us say sugar in milk, if the milk is cold, then the sugar will not dissolve in the milk. The moment you heat the milk, you will see the dissolution happens almost instantly. So, the diffusion actually is dependent on temperature, and we will see some more aspects of it when it comes to the solid state diffusion. So, most of the diffusion coefficients in the solids, they follow what is known as the Arrhenius relation, which we have seen d is equal to d naught exponential minus q by kBt, where d naught is the frequency factor, or sometimes it is also known as the pre-exponential factor. Q is activation energy of diffusion. If you write kBt, that means here it is expressed in eV per atom. Sometimes in some texts you will see the delta H is used, which is the activation enthalpy of diffusion. Instead of using activation energy, people also use the term activation enthalpy. And Kb is the Boltzmann constant, and T is the absolute temperature. Now, this is just an example to show here that d variation with 1 by T, it is taken from this particular reference. If d quite often you see that is written as d naught exponential minus q by RT, in that case the q is expressed as kilojoule per mole, where you know that R is equal to Na into Kb, where Na is the Avogadro's number. Please be careful with these expressions because sometimes when you are solving the numerical problems, questions, then if you substitute the wrong expression or you do not take care of the units, then you may end up in the erroneous answers. So, furthermore about this activation parameter, so if you see that Q is basically nothing but minus Kb times dou ln d by dou 1 by T. That means, if you go back to this previous expression, here it is simply that you draw this graph of log d versus 1 by T. So, or here log d versus 1 by T, and the slope of it multiplied by Boltzmann constant will give you the value of Q. Whereas D naught, we have seen when we discussed about the mechanisms of diffusion, can be written as G into F into nu naught A square exponential delta S by Kb, where G is a geometric factor, F is a correlation factor. This is an attempt frequency, which is almost equal to the Debye frequency. A is the lattice parameter, delta S is the diffusion entropy. If several diffusion mechanisms are operative, in that case, D is summation of D comes due to the summation of all these diffusion mechanisms, and for each you can write let us say D1 is equal to D1 naught exponential minus delta H1 by KBT, D2 naught into exponential minus delta H2 naught by KBT, and so on, delta H2 by KBT. So, the effective delta H in that case is weighted average of all the individual delta H. And remember that we have also seen that for the interstitial mechanism, Q is equal to the delta Hm, which is the enthalpy of migration, whereas for the mono vacancy mechanism, Q is equal to delta Hm plus delta Hv also, where delta Hv is the enthalpy of vacancy formation. Why the difference is there? Because in interstitial case, the interstitials are there already. Okay, interstitials are nothing but the empty sites in between the periodically arranged atoms. So, they are always present. So, there is no extra energy that you have to spend to create interstitial sites, whereas vacancy has to be created. There is a certain enthalpy associated with the creation of vacancy because the bonds have to be broken. So, therefore, for the mono vacancy mechanism, the delta Hv also comes into picture. That means, atom first has to find a vacancy, then the question of how easily it can migrate to that vacancy comes. So, therefore, both the terms come into picture here, that is delta Hm plus delta Hv. Now, for the pressure dependence, the pressure dependence, we see that the delta G is actually equal to delta H minus T delta S, where delta H can be further expanded, and therefore, the delta G becomes delta E minus T delta S plus P delta V, where delta E is the change in internal energy, delta V is the activation volume of diffusion. Now, delta V can also be written as del G by dou P at constant temperature. You can check for yourself how this expression comes. So, where this dou delta G by dou P is taken at a constant temperature, that is equal to activation volume. Now, again therefore, the Q, the activation energy of diffusion, which is equal to the enthalpy, has two terms, which is delta E plus P delta V. This P delta V terms is negligible for solids at ambient pressures. So, in your therefore, you see your ambient pressures or not so high pressures, we do not get so much contribution from P delta V terms, but it becomes significant at higher pressures. And therefore, again the delta V is written as minus KBT dou ln D by dou P at constant temperature. That means, this is the diffusion coefficient variation with pressure, plus a correction term which comes because of the variation of correlation factor as of because of pressure. So, this is a correction term which is a fairly small quantity, 0.01 to 0.03 omega, where omega is the atomic volume. So, for example, activation volume for gold isotope diffusion in gold single crystal is 0.76 omega. So, which is a very small number. You can see that atomic volume is a small quantity. So, 0.76 of that is not a very large number, and that is usually the case in a lot of metals. So, if again several mechanisms are operative, then the effective activation volume is the weighted average of the individual activation volumes, delta V1 into d1 by d1 plus d2 and so on, delta v2 times d2 by d1 plus d2 plus and so on. Now, let us talk about the activation volumes of the self diffusion. So, like we saw that the free energy can be written as delta Gm plus delta Gf. That means there is a migration term as well as there is a formation term. Similarly, for the activation volume also there is a migration term as well as a formation term. So, delta V can be written as delta Vm plus delta Vf. So, for example, if you see that this is a rigid lattice where there is a vacancy. Now, when a vacancy is created, actually the change in volume is equal to 1 atomic volume. You have removed one atom. But what happens is, once the atom is removed, the lattice will try to relax around it. It will try to relax around the vacancy. So, you can see a subtle difference between a relaxed lattice and the rigid lattice. You can see the atoms approach slightly closer to the vacancy, and therefore, the overall volume will be reduced. Okay. So, therefore, the formation volume is equal to omega minus the V relaxed due to mono vacancy formation. So, this much volume change comes down. So, this is the formation volume for the mono vacancy. So, you had the rigid lattice. So, removal of one atoms causes a change in the atomic 1 unit atomic volume, but because the neighboring atoms tend to relax around the vacancy, you have this term coming, which is the volume due to the relaxation around the mono vacancies. Similarly, you can write down the formation volume for divacancy also. So, here V F for 2V will be equal to 2 omega minus V relative V relaxed for divacancy. Similarly, if you see for the self interstitials also. Now, for self interstitial, you have a change in atomic volume, which is a negative change, because now the atom itself has come into this. So, it has actually led to a reduction in the atomic reduction by an atomic volume factor omega. However, when a moment or when the atom comes into its own interstitial, the atoms around it will try to move a little apart in order to accommodate the self interstitial better. So, you will see that a relaxed lattice will look like this. So, the bonds will be elongated, and there will be an additional volume change happening because of the relaxation. Therefore, the formation volume of the self interstitial is written as minus omega plus V relaxed into I. In the case previously we saw in the case of vacancies, the relaxation causes a decrease in the volume. In the case of self interstitial, it causes a increase in the volume. So, there is another thing written here which I will come to shortly, what is known as the migration volume. What is meant by migration volume is that when, let me just show you. So, this migration volumes, the delta Vm that is written, what it means is that if an interstitial solute is exchanging a position with this interstitial site, it has to cross through a saddle point configuration. When it is at the saddle point configuration, you see that the bonds are slightly elongated around the particular configuration, and which leads to a change in the volume. This is known as the migration volume. Similarly, when you have the vacancy tracer exchange, then again this is the saddle position. At this saddle position, there are actually two vacancies present. So, again this leads to the change in the nearby bonds, and therefore, it constitutes to what is known as a migration volume. So this migration volume, for example, carbon and nitrogen diffusion in alpha iron, it is from minus 0.08 to plus 0.05 omega. So it can be negative as well as it can be positive. For the substitutional impurities further, if we can write, the D for solute is equal to this Ga square nu naught, which into exponential minus delta G formation term minus the binding energy term also comes, because when you are talking about a solute vacancy exchange, the binding energy also contribution we have to take into account. So this delta Gb is the Gibbs free energy of binding between solute and vacancy, whereas delta Hm is the activation enthalpy for defect in impurity exchange. And F which is written here is a correlation factor for solute diffusion. So the delta V overall can be written as the formation volume for the mono vacancy minus the volume relaxed due to the binding of the solute vacancy pair, plus the migration volume minus a term which arises due to the pressure dependence of the solute correlation factor. Okay. So these are the various terms that contribute to the overall activation volume. So this, you can see this difference Vf minus Vb is formation volume of impurity vacancy pair. Then you have this migration volume and the correct term which is arising from the pressure dependence. So these are the values of the activation volumes that are given for diffusion and ionic conduction also. So you can see, for example, these are very small numbers usually. For example, in copper it is 0.93 to 1.09. For silver it is 0.6 to 0.88. For gold self diffusion it is 0.72 to 0.75. So these are not very large. For example, germanium diffusion in silicon, these are actually negative. For interstitial, for nitrogen it is positive, for carbon it is negative in alpha iron. So depending on the what atom is diffusing and in which structure it is diffusing, the activation volume change. However, the values are not very significantly large as compared to when you try to estimate the temperature effects. Let us look at now very quickly some more empirical correlations between the bulk properties and the diffusion. For example, the most important property is the melting point. So earlier it was believed that the diffusivity of all metals will be constant is one number at their melting point. However, later the refinement suggested that diffusivity at melting point is approximately constant for a given structure and for a given type of bonding. Okay. So it may not happen, actually I will show you later, that the dTm, the diffusivity at melting point, is only approximately constant for a given structure and for a given type of bonding. It's not one number for all the type of metals and alloys and so on. For example, BCC rare earth metals have similar diffusivity and BCC alkali metals have diffusivities in similar range, but these two diffusivities are not equal. So you have a certain range in which the diffusivities lie for BCC rare earth metals and a certain range in which it will lie for BCC alkali metals. But in not like that all BCC will have similar diffusivities at melting point. DTM is actually very large for BCC metals, while much lower for semiconductors, nearly 6 orders of magnitude less. So that again tells us that at melting point, not all types of metals will have same diffusivity. Semiconductors have, due to their bonding, actually have much lower diffusivity values. FCC metals in general, due to their close structure, typically exhibit lower diffusivities than BCC metals. Then the next correlation is between the activation enthalpy and the melting point. You see, for example, here we have tried to schematically shown, if you normalize the activation enthalpy with the melting point multiplied by the Boltzmann constant, you see that the values are similar when you have a similar structure of the metals and similar type of bonding. For example, you have BCC rare earth metals where delta H by KBT lies in this range. For BCC alkali metals, it lies in this particular range. For activation enthalpy is very high. That's why you saw in the previous slide that I indicated that diffusivity is low, because the activation enthalpies are quite high for the semiconductors, silicon, germanium. Then activation enthalpies are on the higher side when you have oxides and the carbides. For FCC metals, it is higher usually than the BCC metals, because BCC have more open crystal structure. Then activation volume and melting point. So some observations indicate that the diffusivity at melting point is practically independent of pressure. So at a melting point, diffusivity does not depend on pressure, and therefore if you write d by dp of ln dTm is equal to 0, you can write delta V is equal to delta H by Tm into dTm by dP. So that means whatever is the sign of dTm by dP should largely determine the size of sign of the delta V also. So for metals, generally dTm by dP is positive. So the activation volume is also positive. For plutonium, dTm by dP is negative. Delta V is also negative in this case. However, this is not a universal rule. For example, for germanium, dTm by dP is actually negative, but the delta V is positive for germanium. So as I said, these are more empirical relations which are applicable for a large amount of systems, but there are always a few exceptions that are possible. So with this, we will end this lecture on the temperature and pressure dependence, and then the next week onwards, we will start talking about the interdiffusion and the intrinsic diffusions and so on. So thank you.